All right, so let's start out with covariate matching. The idea behind covariate matching is pretty straightforward. We know that we have, so this is our like science table, right, of our potential outcomes. This is the observed outcome. We know the problem is that we're missing these outcomes for these people. We only get to see what the potential outcome that's corresponding to the treatment that somebody actually got, and we're missing the counterfactual potential outcome. So with regression methods, what we were doing is fitting a regression model to essentially impute these values. But something else that we could do is we could just notice, hey, there's people in our data for whom their covariate values are very, very similar. And under the assumption of no unobserved confounding, if their covariate values are similar, that means their conditional means these conditional means are the same, regardless of whether or not there's unobserved confounding, if xi is equal to xj. But then under the assumption of no unobserved confounding, then this really is the mean of this, and this really is the mean of that. And so what we can do is just borrow this person's observed outcome and plug it in to be our guess for what would have happened to this other person if they had gotten the opposite treatment. So you can think of it like this: like these two people, they have similar covariates. They're kind of like twins, right? And one twin got the treatment, the other twin did not get the treatment. So we can assume that what would have happened to this person if they had gotten the treatment is what would happen to this person who did get the treatment. So we've matched them together with a quote-unquote twin, and then we borrow the observed outcome from the other person to impute the missing potential outcome from the other person. So that is the basic idea of covariate matching. And then once we've filled in all of the potential outcomes, we just do a plugin estimate, basically, here. So that's nice. This is a little hand wavy, but it still follows from all the same kind of framework that we've been talking about. It's nice because you do get a non-parametric imputation of potential outcomes. So there's no model here at all, right? There's no assumption of linearity or whatever, any of that kind of stuff. But you do have some issues, which is that you can drop data. So here, let's say this person, it appears they got something imputed because they were matched to somebody else. But what if there's people in your data who don't really have good matches? What happens to them? You can drop them. And indeed, when you have really high dimensional data, like, okay, if you have a single covariate x1 and you're trying to, like, let's say age, right? You can always find somebody who's maybe within a year or two of age. But if you have age that you're matching on, you're also matching on gender, and you're also matching on socioeconomic background, you're also matching on disease history. It's going to be impossible to find someone who looks just like a person of interest, except for that they got the different treatment. So this really falls apart when you have high dimensional covariates. And you also then have to start asking about distance metrics. Okay, if they match on like 2 elements but not a third, is that better than matching on another 2 elements but not the first element? So there's a lot of kind of ad hoc choices that need to be made there.